All right, let's get started. So welcome back to another video session on the symmetrical component, right? We're starting with the new chapter. What do we, why do we have to learn symmetrical component, right? I think the symmetrical component is very important to analyze the unbalanced fault. Okay, uh, let me clarify to you what kind of fault that we have discussed in this course. Okay, we have the so-called we have learned in the last chapter about the balance fault or three-phase fault. Another name would be a symmetrical fault. Okay, symmetrical fault due to why do we use the term symmetrical? Because the topology of the fault is symmetry. Okay, you can when we have the symmetrical fault, we see that the disturbance that the phase A, B, and C experiences, right? I mean, the phase A, B, C has the same kind of disturbance or the short circuit to the ground. Okay, the three-phase fault, if we have, gather the statistics or the number of occurrence, so the total number of three-phase fault is less than 5%. So it's rarely happen. Okay, this is the key. This is rarely happen. Okay, this is rarely happen. Um, the types of fault that normally occur in power systems is the unbalanced fault. So basically, the unbalanced fault is the fault that the disturbance of the three phase is not the same. Okay, so we can see from the picture on the right side that the first type of unbalanced fault would be single line to ground. So you can see that in this case, just only the line C got the disturbance or short circuit to the ground, while phase A and B are still running at the normal operating condition. So there's still power flow from source to load. Okay, so in this case, the fault just happened to phase C only. So you can that's why we call single, right? Single phase to single line, just one line, short circuit to the ground. So the statistics of this kind of fault, it's about 60 to 75% of the total number of occurrence. So mostly the types of fault that happen to the power system is a single line to ground. Okay, double line to ground, you can see that the name suggests double line. So there are two lines that have the short circuit to the ground. Okay, in this case, that are phase B and C, right? And the phase A is still running at the same, the normal operation. So the number of occurrence is less than single line to ground. Okay, it's about 15 to 25%. The last type of unbalanced fault is line to line. You can see that this is a short circuit between the two lines. Okay, the short circuit is in between the two lines. Line means the carrying conductor, right? The current carrying conductor. So these are the short circuit between these two. Okay, so the percentage of occurrence is less as is the least among unbalanced faults. So it's about 5 to 15%. So why are we interested in learning the symmetrical component? Because the symmetrical component here will be the tools to analyze the unbalanced voltage and currents. Okay, we have learned from several courses in basic power system is that the main assumption that we have made in learning three-phase power system is that the three-phase are balanced, right? Most of the times that we talk about the three-phase, so we assume that the system is running in balanced condition. In balanced condition, that's why we could analyze in per phase, right? We could, when we want to analyze a circuit, we normally use the per phase analysis. Okay, that was an assumption that we usually use. Okay, but what happens if the system, you can see that we have this kind of fault. So the operation of the power system is no longer balanced. So when there is no longer balance, you can't use the per phase analysis. So the symmetrical component, okay, is the tool to deal with such an unbalanced condition. Okay, so the symmetrical component will try to transform, right? Basically, I would try to use the term we use the symmetrical component to transform unbalanced, right, system into, right, virtually balanced system. You understand what I mean by virtually, okay? We were trying to transform the unbalanced system, and we are trying to deal with the system which is balanced. So the power engineer, as I said several times, that the power engineer love to simplify things. Okay, that's why we have invented the symmetrical component concept, to transform the unbalanced three-phase voltages into balanced, okay, voltage and current. But of course, you can't directly transform the balance into unbalanced to balance. Okay, it would come with some price to pay. So in this case, when we transform the three-phase voltages, we will have to deal with the so-called zero, positive, and negative sequence voltage. Okay, so basically we try to transform unbalanced to three types of sequences. Okay, three sequences in balance. So you will see in this video, right, how to transform this and what are the benefits of applying symmetrical component. Okay, now you can see from this picture, okay, we are discussing the unbalanced three phase. You can see that in this phasor diagram, okay, the VA, VB, and VCs are of course unbalanced. Why can I say this is unbalanced? Because because of two properties. Okay, the length of this voltage, okay, the length of these three voltages are not equal. Okay, and the first thing is that the magnitude of this is different. The magnitude is different. Okay, this is the magnitude of VA is not equal to VB, is not equal to VC in terms of the magnitude, right? Or it could be, I would add absolute for the sake of clarity. Okay, and the second thing is that the phase angle separation. Okay, the phase angle separation is not, right, 120. So this is these are the two conditions that made the voltage unbalanced. So the phase angle separation is not 120. So this is not balanced, of course. Okay. The concept of a symmetrical component is that we are trying to express the VA, VB, VC as a sum of voltage vector 0, 1, and 2, that this 0 would represent by the zero sequence, okay, and 1 is positive sequence, and 2 is negative sequence. Okay, so these are the two sequences that we mean. So we will try to express VA, VB, VC in terms of VA 0, VA 1, VA 2, for instance. Okay. Now this is the picture of the phasor A, B, and C. You can see this is VA, VB, and VC. We are trying to express VA as a sum of the vector between the component of component 1, 2, and the component 0. Okay, can you see this one? VA expressed in terms VA1, VA2, and VA0. Let's take a look at VB. Okay, if you look at VB, VB, you can also express this in terms of positive, negative, and zero sequence, the sum of these three components. Similarly, for VC, right, you could express this in terms of V1 positive, V2, right, negative, and V0 zero sequence. Okay, so let us see the property of each of the component 1, 2, and 0. Okay. Now I will try to highlight this to you to make this clear in just one slide. Okay. Now you see from the for example this V1, right? You can see that the V1 here, VA1, VB1, and VC1. What are the property of when we compare just the positive sequence? You can see that for VA1, VB1, and VC1, the length of these arms are equal. Okay, the lengths of these are equal. Okay, VA, VB, VC in positive sequence, and the phase angle here, the phase separation, is 120, 120, 120, and 120. Okay, and if you can see from here, okay, the positive sequence, meaning that you stand at the zero reference, right, and we rotate the vector counterclockwise, then you see the A phase coming first, right, entering the goal first, following by B and followed by C. Okay, so the positive sequence, or with the subscription 1, right, positive sequence. The other name we call ABC sequence, ABC. Okay, we are standing at the goal in this case, and we rotate in the positive direction, which is the counterclockwise direction here. And you see the phase A, B, and C in sequence, in this sequence. Okay, that's why this is the ABC. Okay, ABC. That is used in that is denoted by the subscript 1. Okay, so let us delete the positive sequence. Okay, in this case, you see what we mean by positive sequence. When the negative sequence, negative, okay, I will change the color, maybe in purple. Okay, V2 negative sequence. So the negative you see from the subscript 2, subscription 2 to VB2. Where is VB2? Is here, right here. Okay, and VC2. Okay, if you see these three vectors, right, you can see that let me draw this vector here. VC, you will see the VC is point down here. Okay, and VC2, VA2, and the VB2 is pointing in this direction. So this is VB2, VB2. Okay, from this picture, if you rotate this, in the same idea, we rotate this counterclockwise, and we stand at this goal, right? You can see that the phase A just enter the goal first, so the A first, followed by C, and it's followed by B, right? So the sequence that the phase voltage, right, just enter to the goal is in VCB sequence. So this sequence ACB is called negative sequence. Okay, next is called negative sequence, or ACB sequence, right? And this is the the negative sequence. So what do we understand by the zero sequence? Now the zero sequence, you would see, right, the first one is simple, VB, VA, VB, and VC. Now you see that VA, VB, and VC are pointing in the same direction, even but this is a rough drawing, but in this is just approximation. So A, C, and B are in the same direction. Okay, So now we can just decompose this picture into the three components, right? The positive component is A, A1, VB, and VC, right? Or this is A, B, C sequence, okay? Whereby you have the negative sequence, we have A, C, and B, okay? This is A, C, B sequence. And the zero sequence is the sequence at which the angle separation is zero. Okay, that's why this is called a zero sequence. Okay, now you can see that with the unbalanced waveform, okay, with unbalanced phasor, A, B, and C unbalanced. Now you can express this unbalanced phasor in terms of three components of balanced phasors. Okay, these are the balance. So the balance means that okay, the length is the same. When we say balance means the length is the same, okay, and the angle separation between these faces are the same. In this case, the angle separation, the magnitude of the angle separation is 120. This is 120, and the angle separation here is 0 because it's parallel, right? So the concept of balance, right, would line into equal magnitude, right, for the phasor, equal magnitude and equal angle separation. Okay, either this angle separation can be 120 or 0. Okay, this is the definition. All right. So these are the explanation, right? The zero sequence, we use the term zero phase displacement, or it can be a separation. Okay, positive it's either positive and negative could be plus or minus 120 and the equal magnitude. Okay, these I have already described. Now, this is the question, in order to transform the unbalanced phasor, VA, VB, and VC, we want to express this in terms of VA0, VA1, and VA2, VB, similarly, VB0, VB1, and VB2, VB2. Okay, for VC, we want to express in zero, positive, and negative sequence. So the question now is, sorry, what are those components? What are those three components for each of the three voltages? Okay, now you end up, you want to find VA0, VA1, VA2. We want to find these 9 variables, but these are impossible because, you have 3 equations, but you have 9 variables. So you have to reduce somehow, we have to reduce the number of variables, okay, by using some geometrical property. In this case, it is defined in terms of the A operator, which will be explained to you. Okay, now you see we have to group the zero sequence component because this is all these 3, right, with the subscript 0. We call this the zero sequence component, positive zero sequence component, and negative sequence component. We have to analyze the components of each of these 3 groups. Okay. Now if we define the A operator in this case, okay, the A operator is like a unit vector, right? This is a unit vector with the angle displacements of 120 degree. Now we define A is the unit vector of the magnitude 1 with the angle 120. Okay, if you have this 120, everybody knows that the A here is the it can be expressed in terms of rectangular coordinate with negative a half plus j square root 3 divided by 2, which is the A over here. 120 means that this is 60 degree, okay, 60 degree, and you can see that this lines in quadrant 2, okay. That's why we have this is negative part plus the positive imaginary part, okay. If you define this as a and the a square would become a and the angle of 240, okay. You rotate this with another the angle of 120. Basically you just rotate this counterclockwise, okay. So this would lie in the quadrant 3 with both negative real and imaginary parts, okay. So these are the two operators that will use to transform this equation, right? And we transform this to reduce the number of equations into from 9 to 3, basically, because we have just 3 equations, right? We will transform this equation into 3, okay? 3 variables, okay? If we analyze the positive sequence component, okay, the positive sequence component looks like this: VA here, VB here, and VC here. We express this VB and VC in terms of the A operator. So everybody knows that the VB here is the rotation from VA in the positive direction twice, right? Twice time. One time rotation results in 120 degree phase shift. You can see that VB in this case, you have to rotate 240 degree. So you have to multiply the VA, right, by A square in order to achieve VB in positive sequence, okay? So VB here could be expressed in terms of A squared times VA, okay? While the VC, right, VC would lies in this position, okay. In order to get the VC from VA, you just rotate just once by the A operator. You just rotate counterclockwise just once. So you multiply VA by A operators in order to get the VC. Okay. Now you can express VC and VB in terms of VA. Okay. So let me write in this line. Okay. You can see that your VA phasor of VA. Okay, it can be expressed in this form, right? You can express this format right here. You can express this column, positive sequence column. Okay, now you can have VA1, right? So VB, right? You can express your VB by what? A square VA1. Okay, while we see here the third line, you can express this in terms of A V1, VA1 plus. Okay, now you have reduced the number of the variables from VA1, VB1, VC1 in order to just VA1. Okay, you can have just one variable in this column. Okay, you can have just VA1 in this column. Is it okay? Now let us continue with the negative sequence. The negative sequence, you see, no, with negative sequence, it looks like this. So the VA, if you want to get the VB, right, you just rotate this by just once by the A operator. So VB just A times VB just A times VA. Okay, and from this point, if you want to get VC, right, you just rotate twice. Okay, so you multiply this by A square in order to get VC2 from VA2. Okay, this is clear. So for the zero sequence, right, everybody knows that the zero sequence, these 3 vectors are the same. So you just express just once. Okay, in this case, right, you can substitute the properties that we have derived earlier, right? You can reduce the number of variables from 9 to just 3. Okay, I have shown you already for this positive sequence term, right? For ABC, you can express this in terms of VA, right? VA times A square, VA times A, and similarly, you can, you know, express the negative sequence, right? To get, in order to get VB, you just rotate once. In order to get VC in negative sequence, you just, rotate twice. Okay, so now you can reduce the three, equation, nine variables to just three. Now you can have this property. You can rewrite this equation in a matrix form like this. Okay, now you can see that the the VA, VB, VC can be expressed, in terms of the V0, V1, and V2. Okay, V0, V1, and V2. In this case, what we solve from this equation, just the magnitude, right? It's just the magnitude of this phasor, the magnitude of the phasor. Why are we interested just the magnitude? Because we know it already that for the positive sequence, right, the angle separation is in this form, right? VA in here, VB in here, right? If we see it's here, this is positive, right? Soon after you know the magnitude, there's no problem to find VB and VC, because the angle just shift by 240 or a negative 120, right? If you know just magnitude, you can define other variables. Okay, for V2 similarly, if you happen to know just the angle, the length of this face of this arm, the magnitude of the face, right? You know the angle straight away. So the zero sequence is not a problem, because the the zero sequence in each of the faces is the same, right? So this is the transformation from right, VA, VB, VC. These are the original quantity. You can have this relationship, right, in terms of V0, V1, and V2. Okay, what are we interested is not like this, right? Because normally when we measure, VA, VB, and VC. Okay, this side. The unknown is in this part, right? This is unknown. Okay, so now in order to know the unknowns, right, you just find the inverse of this and multiply this by on the both sides of the equation. Okay, in order to achieve that, we have to understand a little bit about the complex identity. Okay, complex identity. Now you see that if A is the operator with the magnitude of 1, then the angle of 120, right? You see this is it. This is A. You have seen that this is A. I'm sorry. This is A. Sorry, this is 1. This is A. This is A, because you have shifted this by 120. The angle, the length is 1, right? You rotate twice. You get A square. Okay, every time you put the power, you increase the power by 1, it will shift by 120. That's why if you rotate one more time, right, it will come back to the original position. In this original position, the vector is expressed in terms of 1, the angle of 0. This is clear, right? This is rotation by 3 times, right? This is the 1 time, 2 times, 3 times. 3 times you get at the same position. Once you rotate one more time, you get A to the 4th, then you return back to A. Okay, and this is the identity, common identity. The sum of all these 3 vectors is 0. Okay, or sum of these 3 vectors is 0. Why is it so? I think this has been discussed several times, right? The sum of these two, right? Sum of 1 and A square. 1 plus A square is here, and you plus with the A. Okay, this vector is 1 plus A square, right? The same length with this guy. So 1 plus A square plus A, it becomes 0. Okay, Now, I think this is not the big issue, right? You can analyze this yourself by using the simple mathematics. 1 minus a, 1 minus a, minus a is 1 minus a is this way. So this is minus a. So 1 minus a is right here. This is 1 minus a. So everybody knows that this is an equilateral triangle with 1 1, and the angle here is 120. So this becomes 30 and 30, right? The length of this vector, right, is square root 3 times, right? Square root 3 times of the arm of this guy, and the angle is negative, become negative 30. Okay, so you get this one. Okay, I would just leave this. You can play around with with this geometry, simple geometry, right? But these are the common property. So we use this common property, to find the inverse. Okay, we can see that, from the earlier formula, right? We express the VP, which is the phase quantity. These are called the vector. This vector is called VP, standing from the phase voltage. Okay, and in this case, we in this slice, right, we use the vector vs, which stands from the sequence voltage. Okay, so in short form, we see that the phase quantity or phase voltages can be expressed in terms of a matrix A times the vs. Vs is a sequence component, right? Sequence voltage. Okay, so as I said earlier, that we are not interested in this kind of expression, because we know this guy, and we want to know this guy. We want to solve for this guy. So we have to know the inverse, right? Using the mathematics, we have to play around with the inverse of this matrix. Okay, okay, we have to find the inverse of this guy. The inverse of this guy, A. How much is it? Okay, we have work on this. People have worked on this, so I'm not going to do in the detail, right? So the inverse of this is 1/3 of this matrix. Okay, 1/3 of this matrix. You have to compare. You should compare between A and the A inverse, right? You see that the first row and the first column remains 1. Okay, the way to memorize this thing is the first row and the first column remains unchanged, right, which is 1 in this case. The change just in the rest part. Okay, in the rest part. Now the change is in this way. Okay, the change is just a swap of these two lines, you can see, right? This a square and a becomes on the third row, and a square turns to be in the second row. So the inverse is like this. So remember that if you deal with the inverse, right, if you want to find the sequence component, you have to deal with the inverse. And the inverse of the matrix, right, the matrix will be multiplied by 1/3. Okay, this is the inverse. Okay, now, this is the equation that we have to deal with, right? You know the VA, VB, VC, you know the V phase, right? And you want to find the V0, V1, V2. We want to know how much is the sequence voltage. Okay, so basically you have to deal with solving these three equations, right? These three equations. It's the same equation, but this is written in the matrix form. This is written in three separate forms. Okay, this is a three separate forms. So now you can have you can draw some observation based on what we have learned earlier, right? You can see that if you apply, right, VA, VB, and VC, if VA, VB, and VC is balanced, okay, if VA, VB, and VC are balanced, what would happen? VA, VB, VC are balanced. You can see that VA plus VB We have learned that VA plus VB plus VC is 0. Okay, if balanced, you see it's already several times VA, VB, VC, right? This is positive sequence, right? The sum of these three vectors is 0. Okay, because VA plus VB is this guy here. Okay, this is VB, and this is VA plus VB, right? It's you cancel this guy. So this has become 0. You can see from the first equation that if the sum of these three vectors becomes 0, then this is 0. Your V0 is 0. Okay, so this leads to the first conclusion, right? If you deal with the balanced three-phase system, then there is no zero sequence. Okay, if you deal with balanced three-phase system, the zero sequence is 0. You don't need to analyze the zero sequence network. Okay, you don't need to analyze the sequence, the zero sequence component. All right, because the sum of this vector is 0. Okay, now you could also apply the transformation to not only just voltage but also the current. Okay, so the phase current and the sequence current can be expressed in the same fashion. IP, right, standing from the voltage vector of phase current. IA, IB, and IC. IS is a sequence current, right? I0, I1, I2, I0, I1, I2. Okay, you could also express in a certain fashion, and the same relationship pertains, right? Because you multiply this by the inverse on the both sides, then you find IS based on the known IP. Okay, and this is the similar expression as we showed it earlier, right? Now you could see that for the sequence current, okay, the one third, the coefficient one third, you know, tell us that this is the inverse, right? It comes from the inverse. So we can express I0, I1, I2 in terms of the phase quantities IA, IB, IC. Now again, if the three phases Y connected, right? If it is Y connected, the neutral current, okay, the neutral current is the three times of the zero sequence. Okay, why is it so? Because now you see, if it is Y connection, okay, Y connection is like this, right? The neutral point, okay, neutral is a common point, okay, of the star or Y connection is phase A, B, and C, right? Normally we assume the current flowing into the neutral, okay, IC, right? And the neutral current just flow out neutral, right? Now you see that your IN is equal to IA plus IB plus IC, okay? Your neutral current is the sum of this. Okay, now you see that if you substitute this into this, so I0 becomes one third of IN, or your neutral current is three times of zero sequence. Okay, now this is the observation. So note that the neutral current just equal to three times of zero sequence current. Okay, if you want to know neutral current, okay, you can, if you manage to decompose the unbalanced current into zero sequence, right? Once you know the zero sequence current, the zero sequence current, you just multiply by 3 and you get the neutral current. Okay. For the balanced Y connection, of course, if it is balanced, then the sum of IA plus IB plus IC, right? In this case, a balanced Y connection, the sum of IA plus IB plus IC becomes 0, or you still remember your neutral current is 0. Okay, so your neutral current is 0, so that you don't have any zero sequence current. The line current have no zero sequence. Okay. In any three-phase system with no neutral path, such as delta or ungrounded neutral, the line current have no zero sequence component. If you don't have any neutral path, right? For example, the delta, okay, with ungrounded neutral, the line current have no zero sequence component, okay, because you don't have any neutral. Okay, let us see how we can apply the sequence component. Okay, you can see that for this example, you have VA, VB, VC, VAN, VBN, and VCN. Okay, all these three have the same magnitude, and the angle separation is 120. So this voltage, right, VAN, VBN, VCN is balanced. So this voltage can be, conclude that these are balanced. So if these are balanced, if you want to find the sequence component of this guy, what would you see is that, the zero sequence is 0, right? And V1, okay, which is the magnitude of positive sequence. The magnitude of the positive sequence itself is VAN, okay? The positive sequence itself is VAN. And the sequence component, negative sequence of this guy, okay, of this set is 0. Why is it so? This is a nice transformation. You see that VAN, VBN, if you write in this case, this is VAN is here, and VBN is over here, and VCN. Okay, if you draw from VP, given VP with the length of 277, right? So these three vectors are positive sequence. Once you compute the components of these three vectors, it would say that, the first thing is that you have a zero sequence. You have no zero sequence, which is 0 here. But this would tell you that, this set of phase voltage is balanced, right? The message here is that this, if you have zero sequence, right? You have no zero sequence. I don't want to repeat 200, right? I don't want to say zero sequence, but this is no zero sequence. If you if you don't have zero sequence, okay, it tells you that this is balanced. All right, since the voltage is positive sequence by itself, the VP is positive, so you don't have any negative sequence. This is clear. Okay, so let's just read the explanation that is given here. This example illustrates the fact that balanced three-phase system with ABC sequence or positive sequence have no zero sequence or negative sequence. It doesn't have any negative sequence component, right? Because we gave the positive sequence inputs, we give the positive sequence phase quantities, right? So the return, you would get just, the positive sequence. For this example, the positive sequence V1 just equal to VAN. So soon after you know the VAN, as we discussed, right? So if you know the VAN, now you just add up with the angle shift of 120, so you get VBN, VCN. Okay. Let's just see in a different form. You see that IA, IB, IC, all these trees are balanced, of course, because of equal magnitude, right? The equal magnitude and the current, I mean the phase displacement is 120. Now you can see that IA is 0, IB is plus 120, so plus 120, IA would be here, and IB is here, right? And IC is here. So now you see This is IA, IB, IC. Everybody knows that this is the negative sequence. Okay, negative sequence. The angle separation is 120 with equal magnitude. So this is balanced negative sequence. If this is balanced negative sequence, so everybody knows that there is no zero sequence. Okay, you put this into the calculation, you see that the I0 is zero. It is zero because this is balance. Okay, this is balance. Now you gave the negative sequence, so your positive sequence is zero. This is zero because the input, right, the phase quantities are negative sequence. So the positive component is zero. Okay, this is zero due to the given phase current negative sequence. Okay, because the given phase sequence are of negative sequence. Now the I2 would return to just IA. Okay, just returns IA. Okay, and you just, it's clear, right? You turn the IA and you just rotate, based on the angles of the negative sequence. Okay, it's clear, right? Now, what happens if we have just, unbalanced currents? If you have unbalanced current in this case, you see, this is unbalanced because, IA is 10, okay, and angle of 0, IB is 0. So now you see that there is no current IB, okay. Probably this is due to the what? The series fault. Okay, you still remember? This might be because of the series fault. You just lose the conductor in phase B, right? So there is no current flows in IB. Okay, so an IC is the same magnitude of 10 and the angle of 120. So the problem asks you to calculate the sequence current and the neutral current. In this case, you must have the neutral current somehow. Okay, you see that if you can manage to find the I0 from the transformation, right? The neutral current IN would be thrice of the 3 times of the I0. Okay, now you see the I0 can be defined by this, 1/3 of the sum of all currents, right? The 1/3 of IA plus IB plus IC. Okay, the I0 is 3.33 angle of 60. Now you say that the neutral current, you can answer straight away that is 10 angle of 60. You multiply this by 3. Okay, you multiply this by 3 and the positive sequence. Now, since it is unbalanced, okay, it is unbalanced. So there is no way that the I1 and I2 becomes 0. Okay, if it is 0 means that it is balanced. Okay, now you can do your math, the math yourself, right? So the IA is from this formula. You get 6.667 angle of 0, and I2 you get by plugging into the formula, right? 3.33 angle of negative 60. Now you see that since the unbalanced current, you have both positive and the negative sequence, and moreover, you also have the zero sequence. Okay, because since it is unbalanced, right? The sum of IA, IB, and IC is not 0 anymore. So there is not, it is not 0. So there is a neutral current, right? This is a Y connection. Okay, this is clear, right? So if we discuss the power, what would happen to the power in the sequence network? Okay, we just look into the general formula first. If we have the three-phase load, in this case the impedance load, okay, we want to see how much power is being consumed by this load. Okay, we express the three-phase consumption of this three-phase bunch of load by the multiplication Okay, this is a multiplication between V and conjugate of the phasor current. Sorry, this is the phasor current. Yeah, yes. Okay. The SP standing from this is a three phase, right? Complex power expressed in terms of the phase quantity. Okay, expressed in terms of phase quantities. Okay. So we can see that this is the VAG times I, right? So all these are in complex form. Okay, the sum of all the the phases. Remember, this is unbalanced, right? So we cannot multiply this by 3, okay? Because the different phase has just different voltage, different angle. So you have to find from the sum of the complex power being consumed by each phase. Okay, now you can re-express this equation by the matrix notation. You can see that this is the matrix notation. Okay, the linear sum of this guy can be expressed in terms of the multiplication between row vectors and a column vector. Okay, you just multiply this, but you have to bear this in mind when we write in a short form. Okay, we normally assume, right, that the row vector is in the normal vector quantity, but if you want to express the row vector, you have to just put the transpose. All right. Now VP and IV, VP transpose times conjugates of IP. Now we just want to see, right? Our goal is that we want to re-express this formula in terms of the sequence quantities. So what do we have to do here is that we know that VP is A times Vs and IP is A times Is. So we just put these two relationships in this formula and you get this guy. Okay, you get this line. Now you rearrange this a little bit, right? You just rearrange this because you get A Vs transpose times A times Is conjugate. Okay. Now, since the matrix are in multiplication, you can relocate the matrix. Okay. Now you relocate this to put A transpose with the A conjugate. So you have to see the property of this guy. Okay, A transpose times A conjugate. A transpose times A conjugate. Okay, the people have done this for you already, right? So once you have multiplied these two matrices, what you get is that you get 3 times identity matrix. Okay, 3 times identity. Okay, once you have put this 3 times identity back to the to the original to this equation, you put this back to 3 times identity u. Okay, 3 times u. This is identity matrix. Okay, now you have this equation. Okay, you have this equation. This equation would tells you that SP is equal to 3 times Vs transpose times Is conjugate. Basically, if you see just this term, Vs transpose times Is, this would translate into what? This would translate into S of S, right? S of S standing from for the complex power expressed in terms of sequence quantities, right? Sequence quantity. Okay, so the summary is that the total complex power delivered to the three-phase network, right, equal to the 3 times the total complex power delivered to the sequence network. Okay, this is the conclusion. Okay, if you manage to find the complex power in sequence quantity, if you want to know what should be the complex power in phase quantity, you just multiply this by 3. Now you can see the grace of this equation, right? You have transformed, okay, the unbalanced complex power equation, okay, If you want to just, if you want to analyze, if you want to find the complex power for any unbalanced circuit, right? What you have to do is that you have to analyze phase by phase, and you have to sum up all those complex power. Okay, this is the direct method. Okay, the better method, or the transform method, is that if you manage to know the power being consumed by the sequence component, which is, what, in the sequence network, everything is balanced, right? Once you transform to the sequence network, okay, everything is balanced. So you just multiply this by 3, then you get the total current, total power. Okay, so this expression is just like, the one that we have made for the balanced three-phase power system. All right. Let us do one example in order to wrap up this, the first clip, right? The power in sequence network is that, if you have the SP, you calculate the SP, which is the complex power in phase quantity, and SS delivered to phase current, three-phase source. In example 8.6, 8.6 is here. Okay, example 8.6 is here. This is 8.6. Okay, and verify. The problem asks you to verify that the SP is equal to 3 times SS. Okay, so you can see that this is unbalanced, of course, right? VA, VB, VCs are unbalanced because of the different magnitude, and the angle separation is not 120. Okay, and IA is also, unbalanced because you have 25.15, 25.71. These are unbalanced, and definitely because of unequal magnitude, and the angle separation is not 120. Okay, now if you want to find SP, which means the complex power based on the phase quantity, so you need to use these two lines. Okay, you have to use these two to compute the SP. How to do this one? Because just simple, right? VA IA conjugate, right? VA times IA conjugate. Okay, this one, this guy times this guy conjugate of this guy, and you do the same with the other two phases. Okay, so now you get this equation, you get this one. Okay, you get this VA. Okay, now you analyze this in the sequence domain. Now, in order to achieve this sequence domain, you need to transform the voltage, right? VAG, VBG, VCG to this V0, V1, V2, right? This is what you have achieved, okay? And also, you need to transform IA, IB, and IC in order to have this line, these three lines, okay? Now, soon after you know this one, these two, right? You just multiply this with this conjugate of this, right? V0 times I0 conjugate, this becomes 0, plus V1 times I1 conjugate, okay? V1 times I1 conjugate plus V2 times I2 conjugate. You sum up all these, products, all these three products. Once you have this, right, you have this, okay? Once you have computed this to the sum of these three products, you have this one. You can see that, right? In order to get the total power in the phase quantity, you just multiply this by 3, so you get the same number. Okay, you get the same result. All right. I hope this is clear, right? This is quite clear to you. So I will just stop the first clip, and you will see you in the next clip. That would take you just less than 20 minutes. All right. See you in the next clip. Okay, let us continue with the sequence network of impedance, right? You can see that we have learned how to transform, right? How to change the um, phase quantities, right? What I mean by quantities, it can be current, can be voltage, right? How to transform? We have to learn how to transform current and voltage in phase quantities into the sequence quantities, right? You can see that you can talk about V phase, right? V phase is A times Vs, okay? So this is the transformation matrix. You can change the Vp into Vs into Vp, right? But normally, right, we know this Vp or phase quantity, and we are interested to find the Vs, okay? So Vs is simply the inverse of A times Vp, okay? And remember what are the identity of the, the A inverse, right? It will come with the factor 1/3 in front. Okay, they come with the 1/3 in front. Okay, this kind of equation can be, the quantity we are discussing could be voltage or it can be current, right? Similarly, you can write the I in phase quantity, which is equal to A times I in series quantity, or you can, use, right? Is inverse of A times IP. Okay, this this is the, the things that we have discussed, how to transform the phase quantity into the sequence quantity. Moreover, we have discussed the relationship between uh, complex power, right? Complex power divided by, SP, right? S in phase quantity. Now it is becomes 3 times S of S, right? S subscript S. This is complex power in sequence and complex power in phase quantity. This is in phase quantity. These are in sequence quantity. Okay, so you can see that in the sequence quantity, you can see that this is the balance. We can, kind of transform this into the balance operation. It's just like what you have learned with the normal, I mean, three-phase operation, where you just analyze where you can find just the complex power consumed by just one load, and you multiply it by 3, because the three phases are identical, right? And this is what we have seen so far, and you can see that when we give the inputs, right, we have also seen that if we give the VP or IP, right, uh, if this IP, either IP or VPs are balanced, what would you observe, right? If this is balanced, okay, if this is balanced, you don't have the zero sequence. First thing is that you don't have zero sequence. If the voltage or currents are balanced, right? No zero sequence, okay? And if you give, right, the VP, for example, VP, you give positive sequence, right? Positive balance. What would you How would you describe this one in terms of the sequence network? If you give VP positive balance voltages, right, you can see that your V0 becomes 0, and your V1, there's something with V1, right? V2, which is negative sequence, is 0, okay? So you don't have, you have 0, or you don't have positive or negative sequence, but you have just, the a positive sequence. This is the, if you give the balance input, right? This is the things that you have learned from the previous clip, right? Now we are going to develop, the sequence network for impedance loads, okay? Now, if you see the impedance load, that we have to start with the voltage equation, right? Now you can see that we have one three-phase load, which is shown in this picture, right? You have a Y connected load. Okay. Now we can describe the relationship between voltage and current by this equation. You give, for example, you see the VAG, which is voltage of A phase with respect to the ground over here, right? If you use the KVL around the loop, right? around this big loop. For example, we have this IA is flowing in this direction, okay, and it will go back to this closed loop, okay. So you basically you have this equation, right? You have the KVL around the loop, okay. The loop is given in this form, okay. This is the loop, okay. Now you can see that the VAG itself is CY times IA because IA is flowing in this direction, and plus Zn times In because Cn is flowing on the neutral path back to the source, right? Now you can substitute the equation. Can you see that what's the purpose of the neutral? You know the neutral is the path, right? That the sum of the current will flow into it. Okay, if if it is a balanced condition, if this set of load is balanced loaded, right, the IA plus IB and IC, right, or the I neutral is become zero. This is IN. Okay, if it is balanced loaded, there is no current in the neutral path. Okay, but in this case, this is in general formulation, so you just put IA plus IB plus IC as IN. Okay, now you can express, you have components of IA and you have coefficient of CY and CN in front. Okay, that's why you can develop this equation 8.2.1. So you do the same thing with the the phase B and phase C. Okay, before the phase A and phase B and phase C, similarly, right? We start with the phase B, for example, right? We start with B and we go in this direction, and you go back and you come back to the closed loop like this. So this is the KVL around the phase B, right? Which is here. Okay, you can rearrange and you can see that once you are considering any loop, right? For example, you consider the phase B, the neutral impedance Cn will play into the picture, right? Now you see, if you consider the phase C, right, VCG is equal normally, CNIA plus CNIB, because this is the IA and IB, or this is due to the neutral current flowing through the neutral impedance, right? And the Cn times IC plus Cy. Okay, now you can see that the component itself, right? If you write the matrix for write the three equations, if you write the three equations in the matrix format, now you can see that the matrix, right? The impedance matrix here, okay, the diagonal of this, right? Diagonal of this matrix will have the component of Cy plus Cn, while the diagonal elements, right? The diagonal elements are Cn only. Okay, these are the Cn, right? So now you can see, okay, you have the equation between V A with respect to ground, V phase A with respect all these bus voltages with respect to the ground. On the other side, you have IA, IB, IC, right? So in this case, you have the voltage in phase quantity. In this side, you have the current in phase quantities, right? So this is the matrix CP, which stands for the phase, the impedance matrix of interface quantity. So you have this compact form, V is equal to C times I in the compact form. What you are interested is that we want to see, right, the relationship of CP in terms of CF, right? The CS here would stands for, the sequence, the impedance matrix in sequence network, right? We are interested to see what is CS, okay? The CS, what should be the CS? Okay, now that's why we put the transformation in on the two sides, right? VP is expressed by AVS and IP is written in terms of AIS. Okay, now we do the sum of the manipulation on both sides. You have AIS on the left, so you multiply by inverse of A on both sides, right? A, you can see that A inverse times A, right? It is identity, of course, right? This is an I'm sorry, this is not identity. This is not the normal matrix, right? So this is A inverse times A, okay? And that's why, you have VSV on the other side, VS the sequence voltage. On the left, on the right side, you have the sequence current. So basically V is equal to C times I. So this is the CS, or sequence impedance, right? CS. So you can have the CS. So the CS here is in the relationship of, A inverse times CP times A. So now we want to see, right, what are these, what is the A inverse times A. Okay, that's why we put this equation CS. All right, we put the CS is equal to A inverse this guy, right? This guy is A inverse, this guy is CP, right? And this guy is, A, right? You multiply all this, okay, and you use the complex identity that we discussed in the table, if you still remember, right? And you just manipulate this, and the result of this calculation is this guy here. Okay, now you see the after performing the matrix multiplication, okay, and use the identity, so the sequence impedance can be reduced to this form. Now it's interesting. If you see, you have CS with just, diagonal elements. So we have just diagonal elements, this these three, because non off diagonals are all zero. Okay, off diagonal are all zero. Now you see that the on diagonal elements, you see just the Cn will play just in the first row of this. Okay, you see this is just on the first row. If you put it back, right, to the original equation, you remember Vs is equal to Cs times Is. So if you put this on the left side, okay, of this equation, this would be V0, V1, and V2, right? On the right side, right, this guy here is the CS. Okay. On the right side, if you put V0 in as the first element, so this guy is I0, this guy is I1, this guy is I2, right? Now you see, okay, if you multiply this, you want to get V0, so you multiply this row by this column. So you see that V0 is Cy, right, plus 3 times Cn, okay, and you multiply by I0, okay, where, the V1 here is the Cy times I1, okay, and V2 would be Cy times I2, right? What is the conclusion? You can see that in conclusion, okay, the impedance of the neutral, right, the neutral impedance, we play the role just in the zero sequence. Okay, we play the role just in the zero sequence. This is very important. You still remember that if we have the balance operation, we don't have the zero sequence. Okay, and if you work in the if you have the balance current, you don't have, the neutral current, you don't have any neutral current. So you can see that if the things, if the system is balanced, the zero sequence doesn't play any role. So does, the neutral, okay, the neutral impedance. I mean, if we don't have any unbalanced situation, so the neutral doesn't play any role. Okay, that's why here the Cn is in the zero sequence only. All right. So you can see that the CS, this is very nice, calculation. The CS, or the sequence impedance, is diagonal, and it can be written in uncoupled equation. This is important. This is uncoupled equation, meaning that the each of these sequence network, right? We will see later, this zero sequence, positive sequence, it can be written in the different networks, right? It can be written in the different network. Let me remind you a little bit. What's the difference between network and circuit. Okay, network versus circuit. What is the difference? Okay, if we talk about circuit, right? Circuit must be a closed path. Okay, meaning that if you talk about circuit, it must be source. You may have a transmission line and you connect to the load. So this is the what this example of the circuit. This is the generator. You have the load and you have, I'm sorry, this is line and you have the load. This is circuit because the current starts from here and come back to the same point. So this is called circuit. If there is a network, right? Network, it does not it is not necessary to be the closed path. So it's not necessary. Okay, it have to not. It is not. Okay, it is not necessary to be closed paths. This is the network. So basically, the network can be just this, right? This is already called the network. Okay, you have just source, you have one element, and this is not connected back to the source. So this can be called network. Okay, this is called network. That's why you can see if you talk about the network. Okay, you can see that this is the uncoupled network because what? Because the V0, right, can be written in terms of Cy plus 3 times Cn. We will discuss with this later. Okay, we will discuss with this later. So now you can see, the three separate equations can be written, and these are the nodes, right? The zero sequence voltage depends only on the zero sequence current, right? So that's why the V0 is uncoupled from I1 and I2. So that's why this is called uncoupled equation. Okay, so you may write why this is uncoupled because the V0 is governed by just the I0 and the impedance. So it is uncoupled from I1 and I2. Okay, from I1 and I2, meaning that if you say about the zero sequence, so it all depends on zero sequence quantities. Okay, this is why uncoupled. So the impedance of which, right, Cy plus C times Cn is called zero sequence impedance, so C0, okay? And positive sequence depends on just positive sequence current or I1. So it is uncoupled from I0 and I2. Okay, and we call C1 is equal to Cy. We call this is positive sequence impedance. Similarly, the V2 depends only on just I2, right? It's uncoupled from I0 and I1, and the negative sequence is called Cy, right? So this is called this is represented by three different networks like this. Okay, so these networks is you can have a different the network represented uncoupling, right? We have V0, we have I0, we have Cy 3 times Cn, right? And separately we also have V0 with V1 I1 for the positive sequence network, right? We have negative sequence network, which is a function of V2, I2, and Cy, which is C2 in this case. So all this is uncoupled to each other because the V2, V1 is not governed by the parameters in zero sequence network or negative sequence network. Okay. So each of these sequence network is separated. That's why it's called uncoupled. Uncoupled from the two others, right? The separation underlines the advantages of the symmetrical component because we like power generalize the thing to separate, right? We want to separate things and we analyze a simplified system. Okay, so the neutral impedance doesn't appear in positive and negative sequence network. Okay, in this picture. This shows that the positive or negative sequence network currents do not flow in the neutral impedance. This is important. Positive and negative sequence do not flow in the neutral impedance. So we don't have any neutral impedance, or in other words, we don't have neutral impedance uh, in in the positive or negative sequence, right? So the neutral impedance itself is is a multiplication of it's a three times higher than the neutral impedance. Okay, so the voltage, right, across this is the voltage across the three times Cn is the voltage drop across the neutral impedance, right? Because you know that the In is equal to 3 times I0. Okay, this is clear, right? I hope this is clear because the neutral current, right, is 3 times I0. Okay, neutral current is 3 times I0. Okay, that's why, you know, the voltage drop across the 3 times Cn is the voltage drop across In times Cn. Okay. Now, what happens if you have no neutral? Okay, you can see that if you have no neutral, meaning that your Cn is zero. Okay, if you don't have a neutral path, right? The Cn is zero means you just remove the Cn out of the zero sequence network, right? But what happened to the delta connection? For the delta connection, the reason why we are talking here, you can see that when we don't have the Cn, or we have open neutral, right? We have open neutral. With open neutral, just remove the neutral because you don't have the Cn, okay? But if you have delta load, right? Delta load, there is no neutral for such things, okay? So it will change in your zero sequence, okay? Now you can see in these two pictures, the positive and negative sequence network remains the same for both of the kind, okay? The change of topology of the load, right? If you don't have a neutral in the Y connection, right, you just remove the neutral, okay? But what happens if you have the delta? Okay, in your delta, right? Let me explain this way. You know, this is the complete circuit. The delta itself, it's a complete circuit. Okay, so that's why if you have delta on each of the sign, you do have the zero sequence in the closed form like this. Okay, and there is no short circuit, right? There is no path going back to the ground. It's just a short circuit. Okay, this is a representation of the delta. Okay, in this case, all right. What happened to the sequence network of a series impedances? So the series impedance is the representation of the transmission line. If you remember, these are something like this is the transmission line. Okay, so you can see that if you express this original phase quantities in terms of series symmetrical series impedances, so you can see that this is a result, right? The zero sequence, positive sequence, and negative sequence are all in series, but with different mutual impedance. What do I mean by mutual impedance? Because CAA here with the double subscription, it means that this is the impedance of the phase A itself, right? Okay, what do I mean by CAB? So the CAB is the mutual impedance between phase A and B, right? The mutual impedance between phase A and B. Now you can see with the zero sequence, right? The zero sequence, it is all depends on, first zero sequence, positive sequence, or negative sequence, right? It will start with CAA, okay? But that if there is a mutual impedance, that will play the role in positive, I mean the zero, positive, and negative sequence in this fashion. You can see that in the zero sequence, right, it would add up, the mutual impedance will be added up to the self impedance by twice. Okay, whereby the positive and negative sequence, the two impedances are the same, okay, which comes from the which can be derived from this the difference between the self-impedance of the phase A to the negative subtracted by the mutual impedance between phase A and B. Okay, so we just give this result. Just want to, I want to just let you know that we have the sequence network in all the components of the power system. All right. So what happened to the rotating machine? Okay, you see from the section 8.2, right? You see the impedance of the load in three phase, right? And we saw the impedance of the transmission line, the sequence impedance of the transmission line, right? We talk about the load and transmission. So now it's inevitable not to talk about the source, which is the rotating machine. Okay, without any derivation, we just give you the conclusion, right? For the rotating machine, the voltage source or the EMF is in the positive sequence only. It's in the positive sequence, okay, where the neutral things, right? If we ground the machine, right, through the neutral impedance. So the neutral impedance will play the role in just the zero sequence. So we just put the neutral impedance Cn into the zero sequence with three times. Okay, three times, because you can interpret it this way, like we have because there is a path, right? The current will flow because the In here is a sum of Ia plus Ib plus Ic. So the In here the neutral current will depend upon Ia and Ib and Ic. So the current that induced in the Cn would be the three times, because of the current, right? Ia plus Ib plus Ic. That's what the three comes from. Okay. For the negative sequence, right? The negative sequence, there is no voltage source connected to it. Okay. This is the wire connected rotating machine. Okay. So this is the explanation that I already explained to you, right? The sequence network of the generator. Okay, we have the internal phase voltage EA, EB, AC. We play the role just in positive sequence component, right? We just play the role in just positive sequence component. Okay, and the voltage drop across the generator neutral impedance is Cn times In. And now you see that the In here, it is Ia plus Ib plus Ic. So it can be written in terms of, since In is three times I0, so you can have this kind of, equation, right? We have three times Cn, which is here, which is C0, okay? Which is the impedance in zero sequence. That's why we put three times Cn in the equivalent circuit over here, okay? This is the this is already explained, and the sequence impedance of the rotating machine are generally not equal. This is the things that we have discussed in the first lecture. All right. Now we have sequence model of the two winding transformer, right? Now you can see that for the two winding transformer, the leakage reactance of the transformer in zero sequence, positive and negative sequence are all the same and equal to the CL over here. CL standing from the leakage impedance, right? The L here is standing from leakage, right? This is leakage impedance. And since we can have different topology of the transformer, okay, you can have this kind of dependent winding on both sides. You can have different connection on primary and the secondary, Y or delta, or you can have either ground or unground. You have different types of connection. So this would affect the the neutral, right? The neutral path. Okay, so we can just apply, you see, this kind of circuit. Okay, when you don't have the neutral impedance, you just remove the you know the Cn, right? The 3 times Cn, or zero sequence impedance, right? C0. Okay, you just remove it. But whenever you have the delta, wherever you have the delta, you just have the closed path like this. So the of course there is a neutral, there is a circulating current inside this load, right? So there must be the way that the current will flow inside internally. Okay, this is represented by the closed path in this way. So you can see that you have Y grounded on the two sides, right? You can have Y ground on primary and ground on secondary, or you may even have different kind of connection on primary and secondary. So this is the representation of the zero sequence, okay, circuit. Okay, now you see, if this is a single line diagram, or the symbol, if the symbol indicates like this, means that the primary is Y grounded, secondary is also Y grounded, right? So Y grounded and Y grounded means that the zero sequence current can flow from primary to secondary. Okay, if you put this primary on this side, secondary on this side, you see that the neutral current, okay, would associate just in the zero sequence network. So you can see that if the two sides are grounded, so the zero sequence can flow from primary to secondary. Okay. Now, if you have the two sides with the same connection, I mean Y and Y on primary and secondary, but on one side the primary is grounded, secondary is ungrounded, right? Primary is grounded means that there is a possibility of the zero sequence current, or I0, right, to flow, right, in the primary side, meaning that if this is grounded, the I0 can flow and go to the ground from this side. So it means that this is a possible, right, to flow on this side, but it is not possible to flow out of the secondary side. So since this is not grounded, meaning that the Cn is 0, so you just remove it. Okay, you just remove the Cn out of the you know out of the circuit. Okay, in this case, so we represent this as an open circuit, right? Now in this case we have a Y grounded and delta. Y grounded here means that Y can go to this side only, and this is delta cannot go on the other side. Okay, for similarly, right, Y, okay, open Y in this case, okay, the open Y in this case, it's just like this, right? It has the same effect as the figure number 2, okay, Y and delta on the other side. Okay, and delta, right, delta is represented by the closed path. Okay, I think this is all for a symmetrical fault, right? I will come back to you, right, with examples, of course, right? This is the unsymmetrical, all right. I will go up to the end of the lecture first, right, and we will come back with a few more examples in different tutorials. So we'll see you in the next video clip. Thank you.